Hello, Accelerated Chemistry students. This is Ms. Krista Foley, and this is your Chapter 2, Section 3 video notes all over elements and compounds. Before we could talk about elements and compounds in more detail, let's talk about the umbrella that they are under, which is called pure substances. Pure substances are matter that has uniform and definite composition. So that means that every sample is exactly the same. They have definite properties, and they can either be made of one type of atom, which we call an element, so iron, gold, or oxygen, or they can have two or more types of atoms that are chemically combined, and we call those compounds. So for example, salt, sugar, and water, those are all compounds. So let's first talk about elements, and there are two kinds of elements that we're going to talk about, monatomic and diatomic. So let's first talk about elements in general. Elements are substances that cannot be broken down. They're the simplest form of matter. They are made up of all of the same atoms. So for example, hydrogen, nitrogen, and lead. Hydrogen is only made up of hydrogen atoms. Nitrogen is only made up of nitrogen atoms. And the element lead is only made up of lead atoms. Now let's talk about monatomic elements to start off with. They are composed of single atoms not bonded to each other. So for example, if we were to look at this picture here, this is an example of the sodium element. And all of the atoms, all of the little gray dots in that picture are all sodium atoms. They all look exactly the same, and they're going to be composed of 11 protons in each of those atoms. Now, there's another kind of element, and those we call diatomic elements. And they are two of the same elements bonded together. So, for example, if we were to look at hydrogen, we write hydrogen as H2 when it's in its elemental form because it's a diatomic element. It cannot exist solo in nature. And there are 7 of these that you need to memorize. So, they are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So those are the 7 diatomic elements that you need to memorize. Because when we write formulas in the future, you're going to need to know how to write the element of bromine properly. It's not Br, it's Br with a subscript of 2. Same thing with oxygen. It's not O, it's O2. If you're very bad at memorizing lists, then you can use this figure to help you. So there are 7 diatomic elements that can be found on the periodic table. Nitrogen is atomic number 7. So if you go to nitrogen and make a 7, so nitrogen over to oxygen, over to fluorine, and then down to chlorine, bromine, and iodine, that incorporates 6 of the 7 diatomic elements, and then hydrogen is going to be the last one. So now let's talk about compounds. Compounds are made up of 2 or more atoms that are chemically combined. So they have a fixed composition, and they can be separated by chemical means to be brought back into the elements that make them up. So for example, carbon dioxide, that is made up of 1 carbon, which is the black ball sphere in the middle, and then we have the 2 white spheres in the picture on the left, or the 2 red spheres on the picture on the right, and those are your 2 oxygens, and that's how we represent carbon dioxide. Now, when you break down compounds, you're actually undergoing a chemical change. A chemical change is a change that produces matter with a different composition than the original matter. So let's look at these 2 examples. So in the top example on the left, if we were to take sugar and we were going to heat it, we would make carbon and water. Carbon is an element, water is another compound because it's made up of hydrogen and oxygen. So that is a chemical change. We cannot go back and undo that. We made something different than what we started with. We could take water and do the same thing. If we ran electricity through water, we would get hydrogen gas and oxygen gas. Both of those have different properties than the water that we started off with, so that's how we know we underwent a chemical change. So the properties of compounds are different from the properties of the element that make up the compound. So for example, table salt, NaCl, is a compound. It is a harmless white solid. However, sodium, which is one of the elements that make up table salt, is a soft gray metal. And chlorine, the other element that makes up sodium chloride or table salt, is a pale yellow toxic gas. But when you put a soft gray metal together and a pale yellow toxic gas together to make salt, you produce something that's harmless, that we use salt on our cooking, for seasoning and stuff like that. And it's very harmless to us. It doesn't make us sick. So let's talk about how to distinguish between pure substances and mixtures. So this is definitely a chart that you should write down in your notes and use for your reference, because this will help you understand how to distinguish between the two types of things that we've talked about. We've talked about mixtures in the section 2 video for this, and now we're talking about pure substances. So when you're talking about matter in general, the first question you need to ask yourself is, can it be physically separated? If your answer is yes, then it's a mixture. If your answer is no, then it's a pure substance. Now remember, mixtures have two categories. They could be a homogeneous mixture or they can be a heterogeneous mixture. And so if you're looking at the mixture, is the composition uniform? Is it the same throughout? If it is the same throughout, then it's a homogeneous mixture or solution. If it's not, it's a heterogeneous mixture. And now let's look at pure substances. These are things, remember, that cannot be physically separated. So it's going to be a pure substance. Can it be chemically separated, though? If the answer is no, it's an element. And if the answer is yes, it's a compound. Just going through and following through this flow chart will help you to better understand and be able to distinguish one from the next. So let's look at a practice problem. This is sample problem 2.2 from your textbook. So it's called classifying materials. So when a certain blue-green solid is heated, a colorless gas and a black solid forms. All three materials are substances. Is it possible to classify these substances as elements or compounds? Now, this is a non-numeric problem, so we're going to solve it in the two-step way. We're going to analyze at first, and then we're going to solve. So let's talk about and analyze this. So let's identify the relevant concepts. So a compound can be broken down into similar substances by chemical change, but not an element. An element can't do that. So heating can cause a chemical change. That's one of the major things that we've talked about. So also remember your vocabulary. A compound is made of two or more elements that are chemically combined. So that is the content that we need in order to solve this problem. So now let's solve this problem. So we're going to apply the content to try and figure out what is going on in the situation. So first, we're going to list the known facts and the relevant concepts. So what do we know from the problem? Let's pull out that key information. We know that we have a blue-green solid and it is heated. Now remember, if it's heated, that means it can undergo a chemical change. So how does that help us to solve the problem? So can we determine whether the substances are elements or compounds? Well, a colorless gas and a black solid appears. So before heating, there was one substance. And then after heating, there were two substances. So what can we determine from this? We can determine that the blue-green solid must be a compound because there was only one substance before we heated it, and then we created multiple substances after we heated it. So that means that the blue-green solid must be a compound. However, we cannot determine whether or not the colorless gas and the black solid are elements or compounds based on the information given. We would need a little bit more detail. So, chemists use different things than what you would think to represent these elements and compounds. So they use chemical symbols to represent elements and chemical formulas to represent compounds. Now, using symbols to represent what matter is nothing new. Back in the early stages of science, alchemists used symbols like the ones below on the right for lead, tin, and zinc to represent elements. The alchemist and John Dalton, who was an English chemist that was around from 1766 to 1844, used drawings to represent chemical elements, like on the bottom, gold, oxygen, and zinc. It was not until 1779 to 1848 where Jan Jacobs Berzelius came around. He was a Swedish chemist, and he based the symbols for the elements on the Latin names that those elements have. And so each element is represented by a 1 or 2 letter chemical symbol. And the first letter of the chemical symbol is going to be capitalized if there's only 1 letter in the symbol. And if there is a second letter, it is going to be lowercase. So some of the Latin names and the English names, when it got translated, are the same, so the element symbols do not change. However, there are some element names that are different than the English ones, so their symbols do not match. For example, sodium. You would think that the element symbol for sodium would be S, but that is not correct. Sodium's Latin name is natrium. And natrium, the first 2 letters of natrium are Na, and that's how we get the symbol for sodium, Na. Copper is the same way. If you were to look at the Latin name of copper, it is cuprum, and cuprum begins with a Cu, and so that's why copper's element symbol is Cu. Now, there is a bunch that don't match up the Latin names with the English names, and so all of their symbols do not look like the names that we are used to. Sodium, potassium, antimony, copper, gold, silver, iron, lead, and tin. Those are all of the English names that did not translate over from their Latin names very well. So let's continue to talk about symbols and formulas. So we've talked about symbols, where the symbols came from. Now let's talk about chemical formulas. Chemical formulas is a short way to represent chemical compounds. So we have element symbols and numerical subscripts that make up a chemical formula. The numerical subscripts tell you how many of each element there is in the compound. So let's look at an example. We have water, H2O. So we have 2 H's and 1 oxygen in that chemical formula. If we were to look at glucose, which is C6H12O6, that formula would tell us that we have 6 carbons, 12 hydrogens, and 6 oxygens in that formula. Now, all of these chemical symbols and element symbols are arranged on what we call the periodic table. The periodic table is a list of the known elements, and they are separated and organized into groups based on a set of repeating properties. Now, the periodic table allows for you to compare the properties of one element or group of elements to another element or group of elements based on where they are placed. So, each element is identified by its symbol and placed in a square, and we're going to talk into more detail as to what is actually in each of those squares. Now, the periodic table, there are 2 vocabulary words that we need to know. So all the elements are listed in order on the periodic table of their atomic number, and the atomic number is unique for each element. And there are 7 periods or horizontal rows on the periodic table. And the properties of the elements will vary as you move across a period, as you go from left to right across the periodic table. There are vertical columns on the periodic table, and we call those groups, and they either are going to have an A or a B next to it. A means that it's a main group element, and B means that it is going to be a transition element. So elements within the same group will have similar chemical and physical properties. Now, this is the end of your Chapter 2, Section 3 video notes all over elements and compounds. And as always, all the information on these Google slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbook, resources CD, and pearsonchem.com. Thank you.